let's talk a little bit about method. So backing up to pre-life, if you will. I've broken the methods out into three different varieties. Really, we can think of them as two. The sponge method and the sourdough method are both what we would consider to be pre-fermentation steps, but let's skip that for the moment. The direct method is that we add our activated yeast directly to our dough and it goes about leavening. And the dough requires significant manipulation where you have to do a lot of kneading to let that gluten develop. In the pre-fermentation methods, let's first consider the Sir Pulich method, in which we mix our water, flour, and yeast in various ratios, but it's very loose, as you can see in my picture here in the middle right. The sponge is a very wet mixture, so high on the water to flour ratio. There's a lot of value in carrying out a pre-fermentation, mostly in the formation of bread flavors, and as well, however, we can establish a strong yeast culture by the exclusion of salt, which can inhibit yeast growth. So we get a very robust yeast culture. We get some gluten formation without kneading, although we still have to work that dough. But here again is a place where you can experiment. An upcoming exercise that you can carry out over the spring break is going to be bread making, and you can see how you can manipulate the formation of the gluten, perhaps with or without using the sponge method. But the more elastic dough that develops in the sponge method simplifies those later steps, such as kneading. But perhaps most important in the sponge method is the development of complicated flavors. Sourdough is also a pre-ferment method. Refers, however, to the complicated, sometimes called native set of microbes that it can develop, or that some people use and hoard religiously. So a complicated mixture of anaerobes that's carrying out the fermentation. Not only yeast, but also bacteria, a variety of lactobacillus, right, lactic acid bacteria. These bacteria are going to be contributing to that acid or sour flavor in this, that's so important to the sourdough. So sour flavor develops as the acid concentration increases. Sourdoughs can be complicated, however, just because of the diversity of organisms that are growing in the dough. The lactobacillus, the acid produced by the lactobacillus, can actually inhibit the growth of the yeast, and that is going to have a dramatic impact on the leavening of the dough. So we see that there's a complicated balance to be struck, and you could also understand then why individuals might be very protective of the sourdough mix that they're using. Now, the interesting thing about sourdoughs is that by taking a piece of the dough and keeping it aside and putting it in the refrigerator or storing it, you can keep that same mixture of anaerobes to use the next time around. In fact, sourdough breads became popular in the United States during the gold rush in California, and there are some bakeries that are still using pieces of that same starter material in their bread today, 150 years later. So we can save a sample for our next bout, of sourdough preparation. So in any case, let's just reiterate. We've got two methods. We directly leaven the dough, or we provide this pre-fermentation that has lots of benefits. Now, one drawback of the pre-fermentation is that it slows the process down dramatically, and especially in terms of industrial bread making, the speed is very important. We want to get our bread into production right away and get it into the stores within a day. So these pre-fermentation sponge methods can be very much slower, and your pre-fermentation can carry on for more than a day, certainly several hours. So a very slow process. Let's talk about bread browning and bread flavor. So this is a complicated set of reactions that I'm going to walk you through here. It's very interesting to see that browning and flavor can be interlinked very intimately. What I've drawn here for you is a set of reactions that are related to the Maillard reactions. You'll hear this frequently in cooking discussions, and I'm sure you've seen it in your text by now. Maillard was a 19th century French chemist, and he did a variety of things, but among the most important was the characterization of the reactions that lead to brown pigment formation in cooked foods. The key in a Maillard reaction is the condensation of a sugar. This might look like a carbohydrate to you with an amino acid. So there's the nitrogen that makes up the amino portion of your amino acid. So the conjugation of those two leads to the formation of this thing called an Amadori compound. Not so important, but what I really want to emphasize in the Maillard reaction is that we require protein, that is amino acids, and carbohydrates to proceed. This is as distinguished from caramelization, which is just carbohydrates. We'll talk about those when we talk about candy making in a couple of weeks. Let's save that thought and stick with the Maillard reactions that are so important in bread making, in grilling meat especially. But what can happen that leads to browning? Well, we can lose that amino acid and form something called a dicarbonyl. So why do I call this thing an alpha-2,3-dicarbonyl? Well, there's one carbonyl and there's another carbonyl. It's a dicarbonyl. However, and so lots of things happen with the dicarbonyl. Maybe most importantly is the formation of this thing, this molecule, where we see, for the chemists in the audience, a Schiff base, which will be important, and you can delve more deeply into the chemistry that's taking place there if you like. The interesting thing is that we can go directly from this Amadori compound to this Schiff base. We can also get there from the alpha-2,3-dicarbonyl with the addition of another amino acid, right? So there's the amino group, there's the acid group, and there's that R group that we talked extensively about in the first lecture that shows you that from which the individuality of the amino acid arises. That defines what an individual amino acid is. So sticking with this line here, this compound, the Schiff base, can readily break apart into something called an aldehyde along with a CO2, which I haven't drawn. So the reaction in this degradation is the release of this as an aldehyde and a CO2 molecule. The aldehydes are very fragrant molecules, very important for the aroma of breads and lots of other foods, as we'll see. But when that aldehyde breaks off, we're left with this carbohydrate and this amino group dangling. What happens then is condensation and polymerization. So this molecule encounters another of its type and condenses, and we form these very important heterocyclic aromatic molecules. So we can form one heterocycle, that is to say it's carbon and nitrogen involved in the ring, but we can also polymerize to form long chains of these heterocycles. These are very valuable for the formation of brown colors. So these large melanoidin pigments derived from what I've drawn here are perols. There are also pyrimidines that we won't look at today. In any case, these large, complex polymers give us our brown coloration. It's worth mentioning that while browning in bread and browning in meat is nice, these aromatic heterocycles can be also very, very detrimental to health as well. We won't go into that today. I'm working outside, so forgive the noise. Polycyclic aromatic hydrocarbons are implicated in many cancers, and they do form readily in the browning of the browning of foods. Again, we'll come back to this when we talk about meat grilling. Let's come back to the alpha-2,3-dicarbonyl, though. When our degradation of our Amadori compound into this dicarbonyl not only results in this browning reaction as well as some aroma molecules, but it also leads to the formation of these ketone molecules. In this one, I've drawn for you acetol, very important molecule in the development of bread aromas. I'm also going to mention another one, which is this cyclized molecule called sotalon, 4,5-dimethyl-3-hydroxyfuranone. Say that 10 times fast. I'm drawing it because it's an important cane sugar aroma, and it's going to come up later in our discussion today, and it's going to come up later in later discussions as well. So a very important molecule. The bottom line to take away from this is that when we mix amino acids and carbohydrates at high temperature, a lot of complicated reactions happen. And I'm drawing, this is actually a relatively simple drawing, just to give you a sense of the diversity of reactions that can take place. But many kinds of complicated polymers form, many aldehydes form. So a wide variety of flavor and aroma molecules and pigments developing just by heating these molecules together for extended periods of time. So the Maillard reactions, responsible for bread browning. Let's look at some other breads, not just loaf breads. Let's look at flatbreads, and I wanted to give you an overview of the flatbreads just to give you a sense of the diversity of products that are consumed around the world. Some of these are leavened, some of these are not. I've opted, unlike your text, to organize these according to geography. So we're moving from the United States, North America, Europe, and outside of Europe all the way to the Far East. I think some of the distinctions that are made in your text are a little bit, well, let's just say that it's not terribly easy to categorize these flatbreads. So I've included some things like pancakes that your text might not include as a flatbread. What's worth mentioning here? First, let me just jump to the tortilla. I only mentioned tortilla used as an unleavened bread in Mexico and much of Central America, made out of maize, right? This is the origins of what we know of as corn. No gluten, right? So we're not going to use corn flour maybe as an ingredient in loaf breads, but not as a loaf bread itself. No formation of that gluten network that's so important for the structure of bread, but still a very wonderful food source. We'll see some more tortillas in just a minute. Bannocks, worth mentioning, Bannocks, a Scottish unleavened flatbread, or at least traditionally unleavened. Now you'll see lots of leavened versions. Again, even within one locale, the diversity of preparations is very, very high. Let's skip down to, what do I want to mention? India, very diverse, right? I haven't done justice to the diversity of Indian flatbreads in this chart, but I just wanted to introduce the idea to you. Sometimes enriched with other ingredients, other times not. Sometimes puffed, sometimes layered with butter to make a more complicated structure and flavor. And even in the Far East, where we don't normally in the West think of bread as being an important part of their diet, the unleavened breads are very important as well, and we'll see some pictures of those in just a moment. Oh yeah, so some pictures of flatbreads. Here upper left we see bannock, the Scottish bread. Here in the middle we see lefse, that Norse bread. Oh yeah, Egyptian baladi. Hopefully we can hear more about baladi on Facebook. But if we look at this is an Egyptian version of pita bread, right? So pita is something that we recognize as stretching all the way from Greece through the Middle East. Even more diversity, carta de musica, that's an Italian flatbread. Not quite pizza dough, even finer and more brittle than pizza dough, but we can consider pizza a flatbread as well. Injera, close to my heart, a wonderful leavened flatbread from Ethiopia. Here we see how it's used actually. And Ethiopian meals are generally going to be communal, and we'll each be reaching in to tear off a piece of the very flexible and injera, and scooping up our other food items and eating them, similar to the way a tortilla is used. But this bread is very flexible. Oh, my mouth is watering as we talk. Also interesting, this is the Persian or Iranian sangak. I stole this picture, I can't remember from where, but it shows you how the size of this bread type, as opposed to something like this, which is more of a finger food. But again, a flatbread. It would be nice to see the griddle or oven that he's cooking these in, but but you can imagine, very large. Oh yeah, so before I leave flatbreads, I just wanted to say this. So flatbreads are everywhere around the world. This is another example of how cooking unites cultures. Even within the diversity of cultures, we see similarities. Here is a photograph of a woman making chapatis in Mahakuta, India. This is a photograph I took in Chiapas, Mexico, a few years ago of a woman making tortillas by hand over a fire. So striking to me, the similarities right alongside the differences in geography and culture and language, etc.